33. Hi, everybody. This is the Physics of Bitcoin show. I am here with Stephen. I'm Giovanni. Today is 9/17/25. I just checked 6,101 days from the birth of Bitcoin. I was doing some calculation and I needed that number. Um, So this show is about basically looking at Bitcoin using the tool of physics, because both Stephen and I are PhD in astrophysics. I always mention that we changed our career a few times, and I ended up doing neuroscience and then finance, studying Bitcoin. Stephen had a path in computing problems and understanding how computing works. Um, and At the same time, we discovered Bitcoin, and it's kind of natural for whoever has a background in physics to look at the world through the lens of physics, because it's a very powerful tool. And like what happened to me when I was working in neuroscience, I made very quickly several discoveries, even a patent, uh, using this approach. Because basically the same pattern that I observed in studying stars and so on, you can find it in the brain. And same thing with the market, and in particular Bitcoin, because it's a very regular system. So this is our approach. Most of the time we present new results, like it will happen tonight, for example. They can be sometimes small results or big results, but it's novel, novel things that sometimes you will be the first one seeing them, because nobody else has done this particular type of research. So we are very, very proud of this show, and how we are contributing in understanding Bitcoin. Please feel free to, the show is supposed to be on X, on YouTube, Twitch, also on Steven. So it's multiple channel, Steven account. You can do questions. We will see your questions in the chat window. Um, I don't know how it works on X, but just make a comment on X. We should be able to see it as a comment. And so if you like to participate, because we mean to interact with our audience, please ask any questions, both on YouTube and on X. Okay. Um, so this is the introduction. Stephen, you want to add anything to this?
No, we do try to come at things from a little bit more fundamental nature. We're trying to get underneath the what and understand the why, and go to more fundamental levels in the analysis. I think today, some results that are new, nothing earth-shattering, but we always try to do some new analysis and new results. And I'm going to focus on gold and Bitcoin's relationship to gold today.
Very good.
So let me share.
Okay.
Okay. This gentleman, some of you will recognize, was Master of the Royal Mint. He's otherwise known to us as Isaac Newton. Most people don't know that he had that job as head of the Royal Mint. There's actually a very good book. It's called Newton and the Counterfeiter. I believe the author's name is Thomas Levinson, but Newton and the Counterfeiter, really excellent book about his time at the mint. And one of the things he did with the coinage was to introduce reed edges. He didn't invent the concept, but it was fairly new. And so he redid all of the coinage to put around reeded edges. And that was one way to cut back on the coin clipping and the counterfeiting that was going on. in the agenda today, I'm going to start out with alchemy. And then I'm going to look revisit the Kelly criterion. First for Bitcoin versus the dollar. And I will look at two forms of Kelly, the investment Kelly, which we're going to end up not really recommending for Bitcoin, and then gambler's Kelly, which is the original formula. And then we'll look at Kelly when you measure Bitcoin relative to it gold, so its price in gold ounces. And the Kelly criterion seeks to maximize the growth of the logarithm of the wealth of a portfolio over time. Then we'll look at the Bitcoin gold correlation, including the lead lag aspects with Granger causality. And then we'll get into the power law, which we've done before, but we'll revisit that and update that for Bitcoin measured in gold ounces. And we'll do something that I've done some of, Bitcoin versus gold bubble analysis, but I'm going to add some color to that. And then something new, which is to look at this mu distribution that Giovanni has been talking about in the last two shows, the previous two Physics of Bitcoin shows, in which one is measuring the local value of the ratio of the change in price to the change in time, or the change in age, really, of Bitcoin, but do it now measured in gold ounces. And we'll see how that shakes out and whether it gives us results similar to the analysis that Giovanni has already shown us for Bitcoin versus dollar. And I'll close with the latest log periodic fits on various time frames for Bitcoin in dollar terms. I think these are always popular in terms of what's happening in the kind of intermediate term out through the rest of the year and into the early part of next year. And I'll even show a chart that does that for gold itself versus the dollar. So let's dive into alchemy a little bit. Well, alchemy, of course, is discredited, right? Because it was an attempt to take base metals like lead and convert them into gold, or to search for some elixir, eternal life substance, and so forth.
It's like the S2F of science.
Well, there's last millennium alchemy, and now we have this millennial alchemy.
Exactly. So like we had a S2F, and then we had the power law of it is a real science, versus
right.
So made up stuff.
Newton is best known for inventing the calculus and for defining, the way gravity works in terms of Newtonian dynamics until you get to extreme conditions of general relativity. So, he did that when he was in his 20s and 30s and 40s, published Principia in 1687 in his 40s. So he spent about 3 decades at Cambridge, but then he had another 3 decades to his life. And he went down to London and he became master of the mint. And he did that for 30 years. He also, I won't say dabbled in alchemy, he experimented in alchemy for decades while he was at Cambridge. And at that time, the distinction between chemistry and alchemy was not so clear, right? Because it was very early days for chemistry in terms of its modern realization. So the analogy one can make is that now we actually have a form of alchemy, or we can make an analogy between the production of Bitcoin and alchemy. And the idea is that you have some prime material, which could have been lead or something in the old version, but now is electricity. You have to have a furnace or crucible, and that is the mining rigs, the ASIC miners, that we have millions of those now distributed around the world. And then you need a catalyst, and that was called, in alchemy, that was called the philosopher's stone. So they were looking for some special substance, and you put it in the cauldron, and you can convert, something to something else, lead to gold or whatever, transmutation. For us, it's the code, it's the Nakamoto consensus, and that is the philosopher's stone. And when you transmute into gold, what you're doing is actually the process is creating Bitcoin itself. So actually, GPT-5 wrote this really nice little sentence. Electricity itself is coined into money, and the philosopher's stone has taken the form of code. There was also this quest for eternal value and even immortality. And with Bitcoin, we know we have what looks to be a quasi-eternal ledger and value. And of course, it improves on gold because it's got a hard cap. Gold is eternal, but it does not have a hard cap. Okay, so that's just a little bit of metaphysics and philosophy, but let's Kelly criterion. Really, the entropy of information. Claude Shannon was doing work in late 40s and early 1950s at Bell Labs, and John Kelly was one of his associates at Bell Labs. And he took the entropy of information concept that Shannon created, and he extended that to the investment situation. He started out with the idea of betting, and you have a bet, and you have a win something, you lose something, and you have a probability of winning and losing, and you have a ratio of how much you win and lose. And by optimizing the log of the wealth over time, it turns out to be optimal because it takes into account compounding and the effect of pullbacks, and it helps you avoid getting wiped out with an excessive streak of losses. So you want to find a way to maximize that log wealth. And if you have a very simple 2-asset portfolio, then the formula is like this in bold. And so you could assume it's cash and Bitcoin, or you could assume it's cash and gold. There's sort of like a base measurement, maybe the dollar. Or, it could be any 2 assets in principle. So what you want is you want to look at the win rate, which is P, the probability of winning on any given bet or time interval in our case. Q is just 1 minus P. And then you want to look at the average win size relative to the average loss size. And that's this parameter B. And it turns out with a little bit of math, basically you differentiate that log wealth in order to find where the curve peaks, hits a maximum, and falls over. The optimal percentage of your portfolio to allocate for a bet, single bet, and in our case, we mean a single window of time, is P minus Q over B. So it's your win probability less the probability of losing divided by how much your edge is. So if P goes up, that's good. F goes up. If B goes up, that's good because the second term gets smaller, right? And you get closer to F equals P. So it's a series of daily or monthly or yearly returns, whatever you choose. This does allow for the possibility of total loss. It is aggressive, but it has a limited chance of ruin. And then the other very critical thing is you have to choose up front the time interval. That's your window. And then you rebalance your portfolio. You recalculate F after you get new data. You keep recalculating F. And you have to rebalance to that new optimal F. So an example, we've got these 2 sources for edge. You want P to be greater than 1/2, and you want B to be greater than 1. Bitcoin has both of these. So let's imagine a simple case. I'm going to play a die game with Giovanni, and here are the rules. I'm going to set the rules. I win if I get even, and he wins if it's an odd number. So we roll the die. The chance that I win is 50%. But because I set the rules, my average win is the average of 2 plus 4 plus 6, which is 4. And my average loss, or his average win, is 3. So I've got this edge. B equals 4/3, right? So P is 1/2. That's an even game, but B equals 4/3. It's not even. So the F is 1/2 minus 1/2 divided by 4/3, and that's 0.125. So if I go into the game with $100, I should bet $12.50 each time, as long as these are the rules of the game and the statistical outcomes for the game. And then if I want to weight it more, if I had a loaded die and P is 0.6, then it would be 0.6 minus 0.4 divided by 4/3. And so it would be 30%. And I could have a much larger bet each time of 30% of my stake or pot. Okay. This shows for Bitcoin versus cash, the investment version of the Kelly formula. What I just showed you was the gambler's version. Now, often if you go onto some of these websites that will do portfolio analysis for you, like portfoliovisualizer.com, and will allow you to put different assets in and different initial weightings, and it'll try to optimize your weightings and get equity curves, and it has a number of different algorithms. If you go check the Kelly formula, it's going to use not the one I just showed you, but this investment version. So the investment version is the difference between the mean expected return minus the risk-free rate, which would be like the T-bill rate, divided by the variance, which is the square of the standard deviation. Now, that's assuming a normal distribution, and implicitly, this kind of formula is assuming some kind of average sort of exponential rise in returns. And we know we don't have either of those things with Bitcoin. Now, since you have very large returns and volatility, at least you want to use the log returns. So that's what I've done here. And this shows this formula, evaluating it week by week over a 10-year period. And you can see it's really noisy. Now, in this particular case, I allowed one to go long or short, and this formula allows you to do that. So it was bounded between, well, actually, I think it was unbounded. So it allowed you to go to over 150%, which would be a leverage long, and it would allow you to go short, as much as 200%. But you can see how noisy it is. Very difficult, to manage a portfolio with something like that. So and in fact, it is more of a short-term tool. So we've just seen that even on the short term, it's kind of too noisy to manage. But let's look at it thinking about, this is still the investment version, thinking about longer term. So I'm thinking about annual, and I want to try to correct for the fact that it's designed for typical exponential financial assets. So what I did for this analysis is I detrended with the power law first to see if that would help things be better. And I also set it so there would be no leverage, but you could go short. So it could be plus 100% or minus 100%. But even on an annual time frame, you get whipsawed. You do make money. If you start at the beginning of 2016 with 10,000, you'd end up with 45,000. 17% compound return. It's not really very good, right? Compared to buy and hold, it's poor. But what's even worse is that after 2017, you would be completely depressed, because in 2016, you'd start with 10,000, you'd more than double it. You'd go into the next year with 22,000. You'd have a fantastic year and end that year with 314,000, and you'd never catch up again. In the next 2 years, you'd lose 90% of your money. Now you're down to 31,000. In the next 4 years, you'd lose almost half of your money. Now you're down to 17,000. And in the last couple of years, you're starting to recover. But this shows how this formula, even on an annual basis, is whipsawing you around. Now, how about quarterly? With quarterly, it actually does better. Because the whipsaw is not as bad, but you're still seeing it. So here I've plotted the equity curve, and it takes you from 10,000 to 120,000 over 11 years, 43 quarters. That's a 25% compounded annual growth. That's not bad. For this test, I didn't allow any shorting, but I did allow some leverage up to 1.5 times the portfolio, but it's very kind of extreme. Out of 43 quarters, it was either at 0 allocation or 150% allocation 39 times, and you had 15 complete reversals. So this is also a very hard curve, to ride. So let's see what the gambler's version looks like. It's better for Bitcoin. And so now let's look the same time frame quarterly. There's again our gambler's version. So despite the name, this is actually a more conservative approach for us than the investment formula is. And what it says is that today, with quarterly decision points, you would have about a 40% portfolio allocation. The chart in the upper left with the gold bars is the histogram of returns. You have a few very high returns, and you have a few quarters when you lose more than half or close to half your money. And then in the upper right is the implied or the determined gambler's Kelly fraction, which is only for the backwards looking data, right? So it's what you keep updating in each quarter as new data comes in. So it rose up to 55%, and then, it's been gradually declining and then stabilizing at close to 40%. And then the bottom chart is the equity curve. This also goes from about $10,000 to $120,000. It's over a slightly shorter interval, about 9 years, because it kind of rejected doing anything until it had enough data to start up. And so it has a higher compound annual growth of 29%. So this one is a lot more manageable. It's about a 40% allocation. Here's what it looks like, though, if you go annual with the gambler's version, and this is a better choice, and it gets you up to about a 67% portfolio allocation. Now, if you went back earlier in time when the returns were wonderful, then it would be an even higher allocation. But, that's sort of behind us and unrealistic. So I started with 10 years ago, $10,000. You end up with $204,000 and a 42% compound annual growth. There were 2 negative years during the interval when you lost, half your money, even though you were not fully allocated, right? So it's kind of good that you weren't fully allocated. You had some downside protection. And the maximum allocation was 73%. The minimum was the starting one at 53%. It started out assuming 50-50 and went from there. And then, you kind of ended up at the 67% level by now. So here we show it on the left. We show the Kelly fraction. Annual is in gold, quarterly is in blue. And you can see how those behaved. The quarterly is pretty stable, around 40% allocation to Bitcoin and 60% allocation to gold. So this is Bitcoin versus gold. And then with annual, you get about 67%. And this shows the equity curves. Quarterly, you grow from starting with 10 ounces, you grow up with the quarterly allocation to 118 ounces. So you get a 30% compound annual growth rate in gold over a 10-year period or 11-year period. And then if you make annual decision points, you would have grown to 526 ounces, 57% compound annual growth in gold terms, while gold has gone up by factors of 3 roughly. Okay, this is Bitcoin versus gold correlation. The chart in the upper left is just the Bitcoin price and the gold price. They're both log scale, but they're shown on the same chart. And there's a huge difference, right? Which is that Bitcoin has gone up by over 100,000 times, whereas in the same interval starting at the beginning of 2011, gold has gone up less than a factor of 3. But this is just to show, to see from the eye, how do they correlate? And they really do not correlate all that well. The right-hand chart shows the rolling 52-week correlation of the, a 1 year weekly prices, log Bitcoin versus log gold. And there does tend to be a little more positive correlation than negative, but it does jump from, higher than 75% positive to lower than 75% negative, and it can do that within a couple of years. Since late 2021, it's gone from negative 75% on a rolling 52-week basis up to 80% last year. And it's pretty positive now. It's tapered off a bit. Most years show moderate to strong positive correlation. And then the chart in the lower left is a measure of the Granger causality. And the question is, does Bitcoin price lead gold, or does gold price lead Bitcoin? And here, you're leading if you get a low score. So it's not Granger causal unless it's below the red dashed line with a p-value of 0.05. That means it has less than a 5% chance of being a random outcome. So Bitcoin does not lead gold price, but gold does lead Bitcoin price. And by looking at different lags from 1 to 13 weeks, it seems like gold leads best at around 2 to 6 weeks. And right now, we're seeing that Bitcoin has not been keeping up with gold. I think people that look at it both know that. This is a regression, both ordinary least squares and quantile regression on the same chart for Bitcoin price in gold over its full history. And for either one, you get a power law index of 5.32, and the R squared is 0.94. The curves are slightly displaced from each other, so the solid line is the ordinary least squares. The dashed green line is the quantile regression at the median, 0.5. And so they do give different values. The trend fair value with ordinary least squares would be 54 ounces now. And with QR, it's 43 ounces. Currently, we're just under 32 ounces. So Bitcoin is clearly lagging gold for now. And we wouldn't see, we're not seeing a bubble in gold relative to gold. We're seeing a trough. I won't call it an anti-bubble, but well below trend. Let's look at the residuals. The chart shows the same thing. Here, the dashed lines on the chart are at plus 0.15 and minus 0.15 in units of log 10 price. The power law trend has been taken out. I took out the ordinary least squares trend. And so we're just seeing the residuals. And right now you're seeing that we are below the lower dashed line. And then I did a bubble analysis. I looked for bubbles of 10 days or longer that are either above 0.15 or for anti-bubbles below minus 0.15 in the residual score. And this is not a z-score. This is the absolute residual score. And there are 12 bubbles, of which 6 had significant length, more than 60 days, and of which 5 had significant energy. But if you sum the energy of those, 75% of it's in the first 8 years, and only 25% of it is in the next 7 years that we've had since then. For the crashes and anti-bubbles, it's similar. There's less total energy. 280 residual days for bubbles, 192 for anti-bubbles. But again, 75% of the energy for those is also in the first 8 years. And Giovanni is going to talk about normalizing this, I think, after I finish my section. Right now, if you say we're at minus 0.24 in the residual, that's 57% of what the ordinary least squares trend is, which is 54 ounces, and it says 31 ounces. And that's right where we are, 31, 32 ounces. Okay, this is the daily slope analysis and also the weekly slope analysis for Bitcoin measured in gold ounces. And more formally, it's called the T-location scale distribution in terms of the distribution that we fit to it. But the histogram is just showing what happens with the raw data.
Did you test it for other distribution just in case? Because I like this one,
no,
but it seems the one that fits better. You see, it's pretty good.
Yeah, I have
pretty
not.
good fit, I will say.
It's a really good fit. It's really good. It's more apparent with the weekly fit.
We need to understand that excess, but I don't know. We need to understand it, why there is that excess at low values. But in general, it's a pretty good model. And I like this because while the regression is complementary, right? It's nice to see it in two different ways. This is pretty independent. Will you agree that it's an independent way of finding the power law, basically?
It's an independent way of exploring the nature of how Bitcoin price grows and varies with time. And so we just look at delta log price over delta log time. One of the things I want to do is put a gap and see what happens if I put a gap of 3 months. So I look today and 3 months ahead and tomorrow and 3 months ahead.
Do you remember I did 4 years ago and 8 years ago, and the two matched, right? I split it in two sections from 2000.
But that's within a chunk, right?
Within a chunk, yeah.
Yeah, no, I don't want to do a chunk. I want to do a span. So I want to take today and 3 months from today and yesterday and 3 months from yesterday and do that for all the data points.
What else I wanted to tell you? And the addition of doing so, there is an additional benefit of doing this analysis that besides getting the average behavior, you're also getting the size of a distribution, right? That will be the other parameters, basically. In fact, with T-location, you get three parameters. You get mu, you get sigma, and you get nu. That is talking about the AV, the tails.
So on the left, we show three numbers. So the first one is this nu, which is a degrees of freedom kind of parameter. And our value is 1.8. Now that's a low value. It's below 3, and it means you have very heavy tails. And it's clear that we have very heavy tails, right?
Can you explain what is meant for heavy tail for the people that don't know?
It means there's a lot more actual observations with large values, either high or low or both, than you would get with, say, a log normal or Gaussian.
With a bell curve. So imagine this applied to height, and there is a population that is described by one of these T-location scale instead of, because usually is described pretty closely with what we call bell curve or Gaussian. Gaussian is a technical term because these distributions are usually named after the person that discovered them or described them. In this case, Gauss. So having heavy tails means you are going to see much larger events because right as we go away from the mean, this applies both for very large and very small event, right? You are going to, in both directions. In this case, if it is a height, it will be a low height and high height. If it is something like this, it will be times when, this value is negative and times when this value is positive. And you're going to see many more of these kind of extreme events than what will you expect if you had a bell curve, because a bell curve tends to decay very, very quickly. So you see people that are, 6'5", but they are very, very few in the population. Imagine there was a weird population where these very large heights, but also very small people were much more common. That's what it means to have a heavy tails. And some distributions look like that, and Bitcoin, for example, looks like that. It means that once in a while we see these very big changes in price in both direction, and they are much more common with what you will expect if it was just a bell curve distribution.
Now in bold, we have the location parameter, which is this mu, Greek letter mu. It's 5.48. Now, I just showed you that the power law, whether you use ordinary least squares or quantile regression, is 5.32.
Yep.
So it's really, really close.
Yep.
If I do it in weekly, I got 4.6. So it's not as close, but it's still within the error
Mm-hmm.
bar, which is 1.4. So it's in agreement, but different.
Yep.
Okay. And now I want to close with the latest on the log periodic power law fits. And I showed some of these last week, and the situation has changed. We've got more agreement between the different time scales. We've got a lower ceiling, than we had before, and we've got a higher floor. Yeah. And also for the 2-year fit, the critical date is earlier. It's actually it's in November. So the chart in the upper left is the 2-year chart of daily prices, and it's showing a critical date in November. It's the first row of the table. Basically, the parameters are A is kind of the maximum of the log price, potentially. The little w, the omega, is the frequency of these waves. And the TC is the critical date at which, something could break or slightly before. And then I give the price objective at TC -3. So for 2 years, it's saying 138,000 in the middle of November. And the error on the prices is about $10,000. And the R squared is very good fit, 96%. The 1-year chart, it's saying early October with a price of 121,000, 6K error, 91% good fit. 4 months, it's saying into January, towards late January, and it has an objective up around 147,000. And in 1 month, it's saying it's now moved. It was very short term, but it's now moved out into October. And this one's downward sloping, but it's saying 114,000. So it's, we've got a much higher floor being shown here. So that's kind of good news. If you take those 4 different price points, being 3 days ahead of the critical time, what it's estimating the price at, then that's plotted in the lower right. So they're all consistent. You could have something that could follow roughly this kind of scenario of, say, $120,000 in early October and a dip during October, and then recovering back up to 138,000 in mid-November, and then continuing on into late January around 150,000. So there's a lot more agreement amongst the different fits now than before, which is helpful.
Yeah, usually this is one of the criteria that is used to select a valid TC. There are some algorithms that do exactly this. They look at different scaling and different time scales, and if you start to see agreement, then it's almost like a filter. You're more sure that probably there is a real critical event.
Good. And just for fun, I did gold versus the dollar.
Yeah, I was going to ask you if you were going to do that. Okay, good.
It says pretty soon, October 3rd, a couple of weeks off, $3,800 is what it's saying right now. That's for the 6 month, but I didn't do any other time frames on that one. So that's it. Thank you. There's a quote from Isaac Newton about truth is ever to be found in simplicity.
Yep, he's right. Our friend, the author of the book Scale, Jeffrey West, says physics is the science of simple, something like that. He has a quote like that. Um, it is weird because many people think that physics is complicated, but it's the opposite, right? We are trying to find the simplest possible. And Einstein also has this quote that says, things should be as simple as possible, but not simpler, right? Not simpler than that.
I thought that was a Feynman
No, it's
quote.
Einstein. I think.
I thought that was
I think Einstein. Maybe it's Feynman.
okay.
One
Maybe
of them
Feynman repeated
is
it.
right. Is a right form. It's a right sentence. Anyway, okay. So I will show my results. I'm continuing this line of investigation, that is basically the idea of looking, this new way of thinking about the power law that I think is much more rigorous way, because the regression is useful as a discovery tool, right? And if it's done properly, there are tests that to show the validity. That is not just somebody making up some curve, or like many people dismiss it. Oh, you found a regression curve, okay, and nobody else found it before in this space, log space. But okay, but I think now a lot of it doubts and resistance should be completely dissolved, by this new approach. Anyway, so I showed it. I'm not going to repeat it. For the people that are interested, they can go and look at our previous show where I discuss how I derived this result. So I decided to go from discussing price with this method to look at the other fundamental parameters that we claim also behave like power law, right? So next time I will do addresses. Now for this episode, I'm going to look at hash rate. So this is the latest fitting for hash rate. Now there is some, and you can see it's a curve, right? So this is one of a way to immediately explain, because many times people show the linear graph. Many often when we have a higher hash rate, people show this crazy curve that goes up like this, and people like it, press the bottom. Oh, I like it, I like it. But they never stop and think, okay, can we describe this process? Very particular. Does it simply go up like some kind of a J, or does it actually follow a formula of some kind, right? And I think nobody ever said it's a power law until I claim that. If anything, people thought it was exponential because it looks like a J, and also it's kind of, you will think that it grows exponentially. For example, a computational power and other digital type of information grow in an exponential fashion. Factually, you can show that some of them grow. For example, today I was looking at a graph of AI progress in terms of solving problems, which actually is a super exponential. So in that case, when it's a super exponential, and even ask this question as a quiz, nobody answer. I don't know why. I show that graph, and that graph of the progress of AI looks like a curve that goes up in this type of graph that is a semi-log graph or log linear graph. So I'm taking the log of the y-axis, linear in the x-axis, and I explained this many, many times, and I will continue because I want people to understand it. If it is an exponential, it will look like a straight line. If it is curve up, it means it goes even faster than an exponential. So, for example, AI progress right now is super exponential. It's really crazy. Bitcoin parameters like the price, addresses, and hash rate, they're not straight line in this graph. So they are not exponential. So even if it looks like a J, this is why you want to do deeper analysis with just doing the linear graph, because our eye is not able to distinguish J's like that, right? Even this looks like a J, but it's not exponential. And an exponential will look also like a J in a linear graph. But the way of distinguishing a real exponential from something that is not exponential is doing this graph. If it is not a straight line, then it's not an exponential. So the next thing they usually do, at least physicists do, is to do a log-log graph where you plot now the log of y and the log of x. And when you do that, you can see it's linearized. Of course, like always, there are oscillations, due to the bubble that we observe. Now, we could debate. In fact, me and Stephen have a little bit of not really a disagreement at point of view, and he could be right, I could be wrong, but he says, and it kind of he has a point that you could say, well, there are two regimes. Basically, up to this point, we follow a particular power law, and then maybe after here, something happened where it's still a straight line, so it's still a power law, but now with a different slope. That could be a valid point, and that happens. Actually, this will be an example that I mentioned many times of phase shift. Maybe something happened at this particular stage where it continued to be a power law, but with a different slope. This can happen. This is one of the things that can happen with power law phenomena. It didn't happen with price, but it could have happened with hash rate. And I think Steve has some ideas about that. What was your understanding of this? Why this is happening?
Well, basically, twofold. Hash rate has benefited from quantum transitions in the choice of the platform. So it started out on CPUs,
Yeah.
then it moved to GPUs, then it moved to FPGAs a little bit, and then it moved to ASICs. And so you got these quantum leaps in performance from that. And then when it started out in the ASICs, the volume was low, and so the technology that was being used, the level of integration was low. And so they've been able to very rapidly improve it.
Yeah.
So I think you had a lot of very large leaps as you went from CPUs to GPUs to ASICs, and then could very quickly improve the ASIC performance.
Yeah.
And in the last few years, it's been more like you're riding the Moore's law for the ASICs performance.
Mm-hmm. Okay,
so there are these kind of dislocations, and you actually see the dislocations to some degree.
Yeah, for example, you can see 1 year, for example, right, where we came down. This is why I want to have more data to conclude that actually there are two shifts. If these continue to be consistent like this for a long period of time, and we see a large deviation, then we can say, okay, there is not one single power law, but maybe a couple. Right now, I just consider it like a deviation, like this one, for example, this deviation was a sustained deviation from the power law, right? And then it corrected itself. So I want to see if there is a correction or if it continues along this path. But we could look at both scenarios. Later maybe I can do an analysis where I assume two power laws instead of one. Right now I'm doing this in a simplified fashion and say, look, there is one single power law. But this is if you do regression, right? The method, well, also in what it follows, well, no, because in what it follows, it doesn't care what is the end of the power law. That is another beautiful thing about this method that I'm going to describe in a moment, because it doesn't assume anything about n. It simply actually finds the n. The only thing that you have to assume that there is some power law that describe the behavior, right? And then it's going to find the n by itself. So it's actually a way of measuring this. In fact, even if there is a change in this n, basically the slope of the power law. So what do we do? So this is the idea, right? If I plot, so I'm looking, first of all, at the rate of change. This is very familiar for physicists because we have all these way of describing parameters in a system. Like, for example, when you take an introductory course in physics, one of the first things that we try to describe is that is also what historically happened, is how motion works, right? Stephen mentioned Newton before. Newton was, together with Galileo, was one of the first uh, scientists or thinker, philosophers at the time. They call themselves natural philosophers, that broke this stalemate that we had for century and century. In fact, thousands of years. For thousands of years, people had no idea. It is so weird, right? Of how to describe moving things. Uh, if you ask, for example, the highest mind in the Greek or Roman civilization, if two stones, one small and one big, were dropped, which one will arrive on the ground first? They will say, "Oh, the large one," and it's not true. It's actually, you can do the experiment yourself, with a piece of paper, of course, right? There is a air drag, etc. But that is a distraction. Like when we study Bitcoin, there are many distractions, and people don't look at what is fundamental. What Stephen say is what people are trying to do with physics. We are looking at what is the most fundamental thing that you can say about this phenomena. And so, for example, with dropping two objects, if they are relatively heavy, so these were two stones, one very large, a big, large stone, and a relatively big but smaller stone, they arrive basically at the same time. It's almost indistinguishable for human senses to separate them. And, even the brightest minds will have said, no, the large stone arrives first, and they were completely wrong. It's crazy. Why didn't do the experiment? Well, it's a simple experiment to do. They didn't believe, in fact, there was some school of philosophy in ancient time that say our senses are not to be trusted. Just logic and thinking needs to be trusted. Our senses can give us false information. It's ridiculous. This is why, okay, it was, great times. We did a lot of progress, but we did more progress in the last 500 years than all the other human history together. Um, So when you study motion, one of the first things that we try to uh, understand and classify, describe in a very precise manner, is how changes are happening in motion, right? So you're describing the position of an object as a certain distance from a reference point. That is your position. When you're talking about velocity, when you're talking about accelerations, and then you build whatever you need to know about what you're studying, maybe an object moving, like launching a stone nearby the earth, right? The trajectory of a projectile, all these kind of things, just using these important parameters like the position, the velocity, the acceleration. And so it's a very natural thing to do in physics, to look at these rate of changes, right? So we are doing this, we are looking at the rate of change. It gives us more information than hash rate by itself. So if you're looking at the rate of change of hash rate, in fact, you can look at also at the rate of change of this quantity that will be the equivalent of an acceleration. So here I'm basically showing the velocity, so how hash rate changes in time. And you can see that it's not a constant change. It's basically it's the same thing that we look at the price. In that case, it's more intuitive. What is that quantity, right? It's the ratio between price today over price yesterday, what we call the returns. So if you add a gain or a loss, same thing here. You can define the same quantity. Basically, is how much hash rate is changing over time. And if it was an exponential, this quantity will be a constant, because that is one of the ways to understand what an exponential is. It's a process where the rate of change is constant, and so over time it gives rise to an exponential. If you combine this quantity, right? Um, in this case, the velocity is decreasing, is slowing down. It's almost like there is some kind of, in fact, it could be understood almost like there is some kind of friction, that this is what happens with motion. If you have friction, the object slows down, it decelerates. So there is some kind of deceleration, right? the changing velocity is decreasing, and it does it in a very precise fashion. So you can see with your eyes, of course, there are, and I never saw a graph like that. I never remember anybody showing a graph like this for hash rate. Uh, and um, there are huge changes because of the bubbles. Things are happening. People, miners get more active during bubbles. I will do this graph superimposed to the price of Bitcoin, so you can see how these peaks corresponds to the different bubbles. But you can see there is a very precise trend, and I draw here in red what is predicted by a power law model, like a single power law model. You can see it's a pretty good fit. It describes even just, we call it, sanity checks or visual inspection, right? It's one of the first things that when you look at data, you always want to see things, want to see if they make sense, to your eyes. The eyes is not the ultimate way to analyze things, but just by looking at things by visual inspection, you can see, okay, it makes sense, right? And this is exactly what happens. And again, it's a much deeper way of doing a regression, because I have a theoretical model. It's just a formula, and superimposing on the real change of the hash rate, and you can see there is a pretty good match. It seems a good model of how these quantities changing over time. Now we can see that right now it doesn't really go through exactly the middle, that basically this corresponds to that deviation, but you can see that it's parallel, like it kind of changed, but it's somehow parallel to these decrease. Now what you can do, right, because it will be nice to find something that stabilize these, and so it is not anymore a function of time, but stays constant time. So basically we do the same thing that we did last time. We take this quantity and then we divide by the log of t, that is the age of Bitcoin, plus one in days, plus one, because we're talking about the value of hash rate today relatively to yesterday. Right? So if yesterday was t, today is t plus one. I take the log of that, very simple mathematical function, and I divide this quantity by that quantity. And if you go through the math that we described last time, that gives me n, that is basically the slope of the power law. But because, so if we follow perfectly this red line, we will get a constant. It will be just one single number, but it's not a single number, right? It's going to change day by day by a big amount, but we are interested in what it does in average. In fact, what it does in average is this. So if I use 120 days, if we calculate this quantity as a moving average, then you can see it oscillates, but it oscillates around a precise value. And this value is this red curve. So, and again, here you could argue, well, kind of it dropped a little bit relatively to that, but it's pretty stable relatively to this. You can see. So again, we are showing that the power law model, even understood as a kind of a statistical process, it's a very good model because it stabilizes this quantity. Basically, we are finding a quantity in hash rate that is not changing much in time. It's very, very stable, and we can study. Now, what is surprising, when we did it, when we did this with the price, we also found out that sigma, that is basically how much this quantity change, right? It's because you can do a distribution. First of all, let me show you the distribution. If I take the entire data history, it can be fit by this t location scale. Again, we see this somehow this excess that we need to understand where it comes from, why we have this excess. But in general, the theoretical curve in red fits the real distribution, that is the blue bars here. Now, um, the width of this distribution, right? We can calculate the total width, that is kind of a compromise, right, for the entire history. But if you want to do it in a dynamic fashion where you calculate it over a moving window, is what you get. But it's kind of the opposite of what we get last time, because last time we got, when we look in a price, let's see if I can show you how this looks for price here. When we did it with price, that quantity mu, sigma, was pretty stable for the first few years, up to basically between 2010 to 2017, for basically 7 years. What do I mean for that? You can see, right, it's oscillating, but you can write, you can draw kind of a line and say, okay, it's oscillating around this line. So this is what I mean, that in average is simply oscillating around a particular value. When in 2017 it jumped, we don't know why. It will be also interesting to see. This was several months. You can see here, right? This is the price, so you can compare it with price. So it happened a little bit, maybe 1 year before the peak. So started to basically during the bull run of 2017. It peaked here, at the bull run. In fact, it was the highest possible value it ever reached. So price was going crazy, right? It was deviating. So this, in this case, this quantity mu, right? It was very, very large, very big gain. So it was kind of a measure of bullishness. It was a bit bullish. Um, even if the distance from the power law was smaller than these other bubbles, in terms of statistical property, it was a bullish bull run that we ever had. Then it went down, because it needs to, during when we go down, right, when we have a bear market, this quantity goes down, but then kind of stabilize it around this. And it has been stable for the last 8 years. In fact, one way to show that is to show the distribution of these normalized slopes, basically these slopes over the years 2017 and 21. That is the black curve. And then the red curve is the years 2021 to 25. So 40 years, starting 8 years ago, and then comparing the last 4 years. And these two curve, the theoretical curve, they basically match. So statistically, price wise, Bitcoin has done the same thing, beside this theoretical decay of the returns. It is a formula, but it's crazy that an asset follows a formula. I know that this is why there is a lot of resistance. People don't want to believe it, but the math shows that this undeniable. If you normalize by this log t plus 1 over t, then you find something that does not change in Bitcoin. But it's crazy. I don't think many people know this, and they should. They This is basically comparing the behavior here, right? When we had this jump. Um, Before that, in a sense, this kind of the acceleration, right? So the acceleration was is higher now than it was in the early history. But it's strange, right? And I think it's because people associate volatility, in absolute terms. And so if the returns are decreasing, the volatility also will decrease. But if you compare it to this, so you account for that decay, then actually is higher now than it was in the early history of Bitcoin, but has been stable over the last 10 years, 8 years. And this is new for the price, right? It is also oscillating around a particular value. Um, what is strange is that for hash rate is actually increasing. So another way of thinking is that it is stable if it is measured in absolute terms, right? It's just flat. But because now we are correcting for this factor of log t plus 1 over t, it looks like it's increasing. In fact, probably we can find a formula. I think it is that log, basically this is what it is, because if you have something flat and then you divide by it and it looks like it's growing, that is basically that factor, mathematical factor. So you can actually calculate how this quantity, I will do that next. I will draw what is expected by the power law. Um, and so it needs interpretation. When we are thinking about this, is basically the change is in hash rate is decreasing over time, but how variable it is in absolute terms stays the same. So relatively to this decreasing value, it seems going up. Um, and I don't know why it stays the same. We need to think about what that means in terms of miners and pools and things like that, right? So the change of a change stays the same over time, but the change itself decreases. And so this is why you see this strange phenomenon. So it's basically the same distribution. So next time, I didn't have chance yet, but I can show you how it looked like 1 year ago, 2 years ago. You can do it maybe every year, and you will see the same distribution with the same mean, but over time, this width becomes bigger and bigger and bigger. That is interesting. So this is where I am. I am curious to do the same thing with addresses and see how that changes and what we can learn from that. But again, this is a very powerful approach because we go deeper now. We're looking at both this quantity mu, that is basically kind of an average slope of long-term behavior of Bitcoin, but also how this quantity changes, right? And it's changing in a oscillatory pattern, right? Because basically it's oscillating around a particular value, but how big of an oscillation, how large of an oscillation, how spread the distribution is, has particular property for the price, and is different from. I was expecting something similar, right? I was expecting that this was flat, but instead it's growing with time. It is interesting. Do you understand this? Do you have any comment about this? Does it make sense?
No, well, no, I don't. I don't think I understand it well enough yet.
Yeah, something that needs to be explored and understood better. But it's very interesting that it has a very seems almost predictable pattern, right, over time. Yeah, and maybe you can try to reproduce these results, and then we can discuss it.
Yeah, I think I may just look at the difficulty numbers because I have those convenient, and just try the
Yeah,
same thing with difficulty.
sure. Yeah, my interpretation is because I do have a graph. I can share that graph. I didn't put it in the slides, but it will just take me a second. Let me show you these. Let me copy these because it's interesting. Okay, let me put it in the slides. All right. So what this graph shows, and you guys are seeing, right? You see this new graph with all the dots, Stephen? Yeah, you
Yes, I
see.
see it. Yeah, yeah.
So this graph is the single. So if I don't normalize, right, and I look at the change, the log of a change in hash rate, I get this. And you can see, again, the red curve is the predicted path for the power law. The black one is a moving average of these dots. So if you zoom out and you didn't do the calculation of a moving average, it will look like it's actually stable, right? That there is maybe a mean that is flat, and then the change around this mean are large, but somehow stable, right? They don't seem to change in time. That if it's correct, the change, but the mean does change in time, right? Like it's basically what, if you zoom in, is what I showed before. It was the graph. Yeah, this one. right? It looks like they are decreasing in time. That that mass is why it's good to use your eyes, but sometimes you have to go deeper and just don't rely on your eyes. Your eyes suggest that hash rate is flat, or we know is now the change is not flat. If it was flat, it will be an exponential, and it cannot be. It's a power law, and we see here very clearly that the power law model describes very well what to expect in terms of the changes. Now, how this fluctuation looks like, it looks relatively stable over time. So how the variability of this hash rate is stable. This is why when we divide by the deterministic factor, the mu gets stable, but the change, of a change grows in time. That is interesting. So yeah, we need to understand that. Is that really the case, right? I mean, the math says so, but why it says so? What is the interpretation of that, right? It's basically how much variability there is in how much the hash rate changes day by day. And that variability,
Mhm.
if you calculated it relative to this quantity that basically accounts for the decay, is becoming bigger with time. So, in a sense, there is more variability in hash rate right now than there was in the past. Why so, and what does it mean, and what it implies is something that we need to understand better. We need to think about it. You don't have any comment on that, right now? It doesn't.
No, not yet. I think I want to go
Yeah,
study it
yeah.
a bit.
Okay, yeah. These are what happens when you do research. You find stuff, you report it, you don't understand it initially, and then it makes sense later when you go deeper. But you see, this is the nature of this show. We present you the results as we found them. Then, in fact, if anybody wants to comment or give any feedback, we, we are open for it. Anyway, okay, let's look at questions. We don't have many. So yes, there is this comment. The volatility of BTC decreases more or less monotonically with time, but the T distribution is stable. It's variety. It is very thin. So if you look at price, the and when you describe it in terms of this parameter, right? This is, you can call it the slopes, you can call it normalized returns. So basically, you're saying, look, the returns, right? So if we go back to what we were discussing with the price, right? Just to summarize, it's a simpler story with the price. It looks simpler. So the idea is the same, but I showed this last time, right? That the returns, I didn't do here a moving average, but if I did a moving average over 120 days, over 1 year, it will be a black line that goes around this red line. This is the theoretical value. The dots are the single value of the returns. It's not easy to see that there is a decay, but if you kind of look far away, you can see that they are decaying, right? If we do a moving average, I'm going to redo. I already did it, but I forgot to put this graph here in the slides. It will look also like this. But in fact, it's kind of on top of that red line. Is why I'm saying the red line really represents how these returns decay in time. That is what the power law says. The returns should go in time. We show these mathematically, right? The reason is because they look like this, right? If the power law is true, and you take the ratio, this is simple algebra, and then you take the log of the returns, that is actually a classical quantity that people look at. It should follow this formula where you have a constant times t plus 1 over t. That is what I mentioned, right? And that's t plus 1 because we're talking about today relatively to yesterday, so it's t plus 1 day. And this quantity, why this quantity is decreasing? Because as you make t bigger and bigger and bigger, so more days are passed since the start, basically there is no big difference. This quantity tends to 1, right? This ratio tends to 1 because right now we have 6,100 days, right? Plus 1 divided by 6,000. It's a number that is much closer to 1 than 101 over 100. If I take 101 when Bitcoin was just 100 days old, the ratio 101 over 100 was a number, bigger than 1 by a bigger factor than it is right now. As this number of days from the start, right, from the Genesis block becomes bigger and bigger, adding 1 doesn't make a big difference. So it's going to tend over time to 1. This number is going to tend to 1. And that means that log returns are going to 0 because log of 1 is actually 0. It's never going to 0 because theoretically this means it's going. And what does it mean log 0? It doesn't mean, it means basically you don't have, the price doesn't go up or down, it stabilizes, it becomes a stable price. But this is probably something that, mathematically will take hundreds of years to happen, and because something big will happen to the economy, to the world before that. Maybe we have hyperbolicization or the singularity, whatever comes first. So it's just a theoretical consideration. So the decays are going. There is a decay, and then the idea is, well, what if I divide by this quantity here? What if I divide the returns, the log returns by this quantity here? And notice that is cool because I don't have to assume any n. I'm going to actually find what is that n in that way. It's really cool. Or what you're assuming that there is some kind of predictable pattern in the long term that follows this formula. And if you are right, then this quantity should be stable. And that is exactly the case because here it is, right? And it's also cool because of the variations around this quantity. This is a moving average that you can see fluctuates around a particular value. And this basically says Bitcoin has done the same thing for the last 16 years. Now, if you're looking at also the quantity sigma, that is how much they change, how much this quantity mu change, so the acceleration for the price, it's the story shown here. This is the quantity sigma. Like I say, I'm basically summarizing to answer your question, to drive this point home. From the beginning, 2010, when we started to get data, to 2017, it was pretty similar. And then it jumped to a little bit, kind of a factor of 2. It jumped by a factor of 2. And then it stays stable. It didn't increase, it didn't decrease, kind of stay stable around a particular value, right? You can calculate what the mean is. I think I calculated is like 140 or something like that. And this is another way. Yeah, okay, here actually, this is what I was discussing before. You see, here I'm calculating the moving average of returns this is done over 1 year. And you can see here, if I just do this quantity, returns themselves, you see how the blue line tell us in a very good way what is the general pattern. And here, if I do this normalization, you see, they are stable. They are oscillating around. This is very cool result, very, very cool result. And I can do the same thing with hash rate, exactly the same thing. The only thing that is different is that I was kind of surprised that this sigma seems to go up, right? Almost like in a linear fashion. You can see it kind of bends a little bit. We will try to characterize what is the formula there. There is a particular pattern, some kind of mathematical pattern, and we need to make sense of that, right? Why that is the case. So the story for mu is very simple. The story for sigma is a little bit more complicated. In particular, if you compare what happened with hash rate versus what happens with price. Next episode, we are going to see addresses and see how that behaves. I think it's going to be more similar to hash rate than price, but let's see. Let's see what happens. And then later we can do actually price versus addresses, for example, because you could do the same normalization uh, for that quantity. So you will not do it versus, so you will take price, the change in price, and then you normalize by the change in addresses, right? Like the theoretical value of a change in address. Yeah, in that case, it's more difficult because it's not really a formula. It's based on the data. I have to think about, but technically, you could do the same thing. Um, yeah, we will have to see. But with time, it's really more direct because with time, it's not something that we empirically measure from the data. We just, we have this clock, right? We know that every day, one day, we have one more day. So yeah, it's a little complicated story for the sigma, but it's very simple with mu. Basically, we oscillating around the value, and this value is decreasing with time. This is probably for you.
Uh, yeah, that was kind of what I was thinking would be the next thing I would look at. I didn't do that analysis yet, so I don't have an answer yet. I might have something next week.
And then this other comment.
Yeah, um, I guess you're getting at the alchemy slide and so forth. People talk about bits and even Bitcoin as if they're not real. Bits are real. They're magnetized regions on disks, or they're charge states on SSD, right? Volatile RAM. So it's still electrons, uh, that are configured in a certain way in hardware and that are readable through electronic means. So bits are electrons, and we talk about atoms to bits. So what we have with Bitcoin is we have atoms to electrons to bits, but they're very special bits. What are the atoms? Well, you have to produce electricity in the first place. So, whether you do it through solar power or natural gas or with a nuclear power plant or hydropower, their atoms have evolved that we then, create electricity with, which is ordered flow of electrons. And then we need atoms to create our mining rigs, right? And then collectively with that, we run our code and we create some very special bits that are highly secured, on the blockchain and then replicated many times, right? Tens of thousands of times around the world on full nodes. So Bitcoin creates very special bits that are material. It turns this raw electricity through code into these very special bits that are encapsulated by large amounts of energy and large amounts of cryptography. And I don't hear other people talk about it in that way much.
Yeah, yeah, it's very beautiful understanding. Very physics like. We did. Did you answer this one?
Yes, yeah, we
Okay.
just answered that.
I think this covers most of it, right? Okay.
Mm-hmm.
Yeah, yeah. So that is entire idea, right? That in physics we make a big deal when we find quantities that are somehow stable. Of course, it's much more like that in physics because we are dealing with the precision, almost computer-like of physics laws. But depends which realm of physics, right? If we're talking about fundamental laws like gravity or electromagnetism, it's super precise in how it works to many decimal places. But then when you're looking at more complex systems, right? Um, things becomes more statistical. This is why we develop an entire field called statistical physics. When we have a complexity systems, where long time ago, it's also called chaos theory. Basically, people realize when there was this dream that everything could be explained like in a Newtonian fashion, with basically formula that you can solve through what we call closed form. First of all, that dream was already broken with the three body problem. Even if you have a gravity and you have three bodies, already you cannot find a formula for that. You have to study it with other tools, solving the differential equations that describe differential equation basically are equation with this quantity that change, right? The velocity, the acceleration, etc. Right? We're looking at changes in time and trying to solve these equations. You have to solve them numerically. You cannot solve them. You can solve them. You can describe what happens when you have three objects. So in fact, today we do simulation with millions of objects like stars and things like that, but you have to do it numerically. And the problem doing numerically is that if you try to do a simulation too far away in the future, any small little error, right, on precision in your initial positions can give you a completely different results when if you add another level of precisions, right? So to the point where if you try to answer the question, will the Earth continue to go around the sun I don't remember what is the record. How far can we go? Like maybe 100 million years in the future or something like that.
Oh, I don't know.
There was even a
I don't
prize
know,
at a certain point. And
but I will mention
Poincaré
one
won
thing,
the
which is
prize for
about
it.
the.
And his
Oh,
answer
okay.
was no, we
Oh,
cannot. There is in fact, it was kind of a beginning of chaos theory. Uh, you can go
uh-huh.
up to few million years or maybe 100 million years, and then it's for sure not billions. So we don't know if the Earth will continue to go around the sun in a billion years from now, or even a 500 million years from now, because we don't have enough information. Any imprecision in how we measure the distance of this Earth and the Sun, the influence of the other planets, etc., can give a completely different result. If you go far, 10 years from now, 100 years from now, we know, but if you go too far in the future, you don't. And so people started to develop other tools based on statistical mechanics, this idea of attractors, where, okay, maybe we don't know exactly what the orbit is because it's chaotic, but it tends to go around this path, statistically. It tries to, and in fact, our power law, in a sense, is an attractor. We have to, in fact, it will be interesting to develop maybe some chaos theory idea around the power law being an attractor. Um, so it's a compromise where, okay, at least we can say something. We can tell that it tends to go most of the time around this particular trajectory versus another one, even if we don't know exactly what happens moment by moment. So it's still a form of knowledge, right? Even statistics is a form of knowledge. It's dealing with the fact that the world is uncertain, but it's not so uncertain that we don't know anything. We know certain things, and that is what statistics tell us. Yeah, you were going to make a comment. Sorry, I interrupted.
Oh, just on the three body problem, one of the primary reasons why the U.S. beat Russia to the moon was because we had computers that could solve the three
Yeah,
body problem
exactly. In any case,
numerically, and they did
yeah.
not at the time. Yeah.
One thing I'm thinking about this distribution, that kind of um, it's coherent with what we described before, is that maybe a better way of fitting these is actually with two distribution, because we know already, right, that it tends to be bimodal above and below the core power law. And so what you see there as an excess maybe is actually the peak of one distribution, where the left side is the Yeah, so we could try to do a mixed model or something, but instead of a mixed Gaussian model, maybe a T scale, a T scale Gaussian model or something. Let's see what we can do. Maybe it's two distribution overlapping, but it does a pretty good job to with one, but we can improve it. It's pretty symmetric, but not perfectly, right?
Mhm.
More work to be done. we, we,
Yeah, we
we,
know it got bunches up in the
this will
core.
give us more
So
episodes.
I think we're seeing some of that.
The Recon is so interesting system that I think we will be here in episode 734 and still talking about new things to discover about Bitcoin. It's really cool. Are you with me, Stephen? Good.
Yes.
So, okay, guys, thank you so much to spend. Oh, there is one more question. Is there a video article can get speed out of the service search? Yeah, both me and Stephen have accounts. In fact, I can show you. I have a. I can. Yeah. So this is my here. It's a the Substack for Stephen, where he posts his research. I post my on Medium, and here you have the addresses for both of them. The websites, and we are in the process, me and Steven, to write a bunch of actually research grade articles, where we're going to explain all the basics. And I'm also having this project of writing an entire book, and probably Steven, if he likes, he will be my co-author of that book. It will be one of these books that is, meant for, how we say, an average reader, but an intelligent average reader, right? That can actually do some simple algebra. They usually say don't never put formula in a book, but we can put one or two formula, simple formula. But yeah, so I will start with this. And also, if you go to my YouTube channel, we have actually a series that we call the Physics of Bitcoin. Beside the show, there is also kind of high production series that I did with my son, where I think there are 5 episodes. Like you can watch them in a sequence. Yeah. So and the channel, the YouTube channel is called Quantonomy. Quantonomy. Okay. Yeah. Thank you for your interest.
Thank you
All
all
right.
for
We
joining.
will see each other next week. Same time, same place. Bye, guys.